Okay, so it's week 2, day 2. It's a very square number when you think about it. Today we're going to continue talking about object-oriented programming, focusing on design. We're going to attempt to do Conway's Game of Life. If it's a fail, I've got a backup plan, but I'd like to show a little bit more about how classes can work together. And Conway's Game of Life is kind of a classic example of a computer programming challenge. Um, I've never really seen it in a job interview question because it is kind of a larger project than you would give somebody, and it is very commonly solved. So if you say, "Hey, here's a take-home code problem," Conway's Game of Life, you could go Google it and have it turned in 800 different programming languages. So it's not really a valuable programming quiz, but it's still an interesting way of thinking about like closed systems, making classes work together, and even grids, right? Because we all have to work with grids eventually. But first, we have a couple of questions about last night's homework. Last night's homework was the Design Your Life object-oriented programming exercise. So take it away with your questions.
So when we're defining these in particular, what exactly is the meaning or value of like self and name?
Okay. Okay. So yeah, I think I see exactly what you're saying. So let's take a look at the code. This is not the code. Let's close that window. So you're saying when you're defining the class and you have self.name.
Oh, I mean even one step up, like next to a name.
Right here?
Yeah.
So in init, so by the way, this is referred to as the method signature, which is it's an abstract term to refer to like all of the parameters that are assigned to that method or function. So it's like these two variables right here, that makes up the method signature. So you're saying like what's the deal basically with self and name here? So self, like I said, with every instance method that we're going to be writing has to be passed in. Otherwise, it will error. So that's like the deal with self is that it's required, and if you don't do it, your program won't run well. It will run, but it will probably break somewhere weird. So self always shows up, and the really screwy thing is that you can really name self whatever you want, but 99.9 repeating 10 times amount of people call it self. So when everybody calls it self, it's self. And name, this allows us to give a custom name to our fighter when we create it. So when we say name here, that allows us to call fighter with a string of Edwin. So if I didn't have name here, so if I just erased name here, I wouldn't be able to pass Edwin or Jim in. Like this would be invalid and it would error on me when it tried to get to it, meaning that my code would wind up looking like this, effectively taking away the functionality that I can't give a fighter a name when I create them. They're all nameless fighters.
So that's like in a sense a variable that you can change after you've created the whole.
Yeah, so when you create fighter with Edwin passed in as its first argument, what we do is we take that name, which is this variable right here, which is coming from outside. Think of your init as like a closed box, like a function and it knows global scope, but it has its own scope too. And somebody from the outside says, "Hey, get ready to be born." It's like a little baby being born, right? And this baby is ready to get born, and it says, "I'm going to." This is probably a little grim here, but it's going to give that baby the name. Let's just go back to the box. Let's not talk about babies. It's going to put a name into the box. And then that box is going to take that name and it's going to say, "I have a name now." And it's going to do what it has to do and assign it to its own name. Whereas before, when we just did this, we've effectively sealed off the box. Nothing can come in from the outside. It gets rejected as an error. And the cool thing is that I can put as many things as I want in here, if I spell it right. So I could put 5 things, I could put 100 things if I wanted. And the more things I put in there, that means that the more configuration I can pass in from the outside world.
So like if you did add age there, how would you relate age somewhere else? Like do you have to define?
So if I passed in age and I wanted to define the fighter's age, what I could do is I could just say self, like you said, self.age is equal to age. And that will say, because self represents, think of the self as like the soul of that fighter. Like that is their brain, that is everything that encompasses that particular one. Not all fighters, but that one that we just created. So this one that we're creating, we had a slot for the name to come in. We named him Edwin. We have a slot for the age to come in. We can say that that's like 35. We pass that in. But the hit points, right? That's not getting passed in. We have to we can't customize the hit points. So in that closed box, we don't allow people to set the hit points when they create a fighter. We say that fighter is going to be stuck with a hit points of 10. And so everything that's set onto self, because you can think of self kind of like a dictionary, but you can just set any key value that you want on it. Like I could seriously set unicorn equal to true here, and I could set whatever I wanted on self. And then that would allow me, so I'm not going to set unicorn equal to true. And since self is getting passed into all of these methods here, I can refer to self.unicorn in any of these. I don't have to pass it in explicitly. It's just available to me. So that's effectively saying in each one of these methods, they have access to the state of Edwin's soul. And that's why I kind of refer to it as a lifeboat, or like just a boat that's swimming or that's going from method to method. This is when you have a boat that's like, okay, I've got a name, I've got an age. For those of you that don't see in the video, I've got like a little piece of paper and I'm just like floating it around. But like, I've got a name, I've got an age, I've got hit points and weapon. I'm in the init. And now over here in my other hand is upgrade weapon. Well, upgrade weapon needs self.weapon. So that little boat floats across as self, and now it's in upgrade weapon. So upgrade weapon can say self.weapon is now fire sword. And each one of these, as long as self is getting passed in, is going to pass around self. And
So we could have a method in there creating a new self dot. So like in the hit method, you could do self dot unicorn. That wasn't defined in init, but you could do that, and then as long as that method has been run on that object, you could then access self dot unicorn.
You can, but that's not a great practice. So the question was, so just to clarify, the question was in hit, even though I don't have self.unicorn defined in init here, I can say self.unicorn is equal to true, which is great because I could just define any self variable or any instance variable I want in any method. But the problem that was brought up is that I have to call hit if I expect any other method to expect unicorn to be there.
So basically, you would assume every object of that class. If you've got 3 objects of that class, and 2 of them you call hit on, you're like, okay, well, everybody's going to have done hit, so they'll have self.unicorn, and then the third one that never did hit, you try to call it, it wouldn't have been created because it never used the hit method.
Right. So we're discussing the pain points of creating new instance variables inside of method. I like to refer to it as you ever work a lawnmower and you have to prime the engine. So before you start the lawnmower, you've got to go pump gas into the engine. That's kind of like what this is. Like if you want to refer to self.unicorn, but you have to call hit first, like that's kind of a code smell that is a problem because, like you said, maybe 2 fighters, they called hit, but one of them didn't. And then later down the road, all 3 of them tried to refer to self.unicorn, and one of them errors out, crashing your program. The good news is that this is easily guarded against by just saying something like self.unicorn is equal to none, or false, or giving it a default value. Like that right there has solved 95% of our problems just by doing that. And that's a drawback of the Python programming language. And remember, I said this in the first day of class, is that you'll know that I know a language very well if I'm going to talk crap about it. So you can take this for what that is worth. Is that there are a number of object-oriented programming languages that are object-oriented first will not allow this at all. This will be completely broken for this to work. In fact, let me see if I can. While I'm talking, let's see if I can demonstrate that very quickly. So what we could do here is we could say self.unicorn is equal to none. That way, it doesn't have to be set to true or false. It can be none if it needs to, but the main important part is that it's defined, is that you need to make it defined. Now, go ahead, ask your question.
So basically, one, I doubt it would work without it, but definitely good practices. So you want everything, at least a base of it, defined in your init.
Yes.
Okay.
Yeah, either in the init or you can define it out here on the class, which we're not ready to talk about. I could say unicorn is equal to none in this like little like gray matter space here.
And that's just true for the whole fighter class.
Yes, but that's true for every fighter class by like even if it's not created as an instance. Like I said, we're not ready to talk too much about this yet. That is valid though. This will work, but I would prefer to see that. So.
Well, I was going to ask about that, but if you want to talk about that later.
Well, we're probably not going to talk about it till later. The main thing is that when you set unicorn up here as none, this sets it on the class, which is different from setting it on the instance. And that can cause a problem when you have multiple instances. Remember, because the instance is like a born baby. Like that baby has been born. It is now alive. We have this thing. Setting this value, unicorn is equal to none, is like setting it on the blueprint. So you're giving this design instruction on the blueprint, and it's really kind of a weird metaphysical concept that the blueprint can have values instead of just instructions. So when you have unicorn is equal to none, you have like a set of blueprints, and you say, these blueprints have a value of unicorn that's none. They also have all of these methods that eventually will set state when it's born. But this set of blueprints has none. Remember, though, that you only have like one set of blueprints. And so I think I'm going to stop it there. It's that it's fine to set these things here, but it can balloon out of control mainly if you're doing things like if you're doing gym.unicorn, you're perfectly fine. But if you're doing fighter.unicorn, remember capital F fighter refers to the class, that will get you into some trouble. Because like if you set that equal to something else, like that, and then you create a new fighter.
Unicorn is going to be that new value you pass it.
Well, we set it here, self unicorn is equal to none. But if I just did this, that means I've redefined that on all of the blueprints, and anything I create after that,
So any
and even
variable
before, I
set
think.
in a init, that's instance specific,
Yes.
whereas the other would be class specific. So any variables you set above a init, those you could, if you change those, it's changing the blueprint. Whereas if you change the ones in the init, it's just changing on the instance.
Correct.
Okay.
Correct. And I think it's much safer to change on the instance because you're only affecting, oh geez, what am I doing here? You're only really affecting that one particular person. Let's see, I should have, let's see, something like this. So while that gets going, I kind of want to show you how it will not allow me to do that, but it's probably going to take way too long. I don't want that to hold us back. So, any other questions? Definitely feeling better. Awesome. All right, so just real quick, so like if I've got a class here in this program, remember that the idea was that if I referred to an instance variable that didn't exist, that I didn't define somewhere else. So like if I was to say static, oh shoot, you know what? Let's do this. If I say I have a void, why is it bumping out like that? Whoa. Void lol, and I set self dot. You know what? This is not going to work well. This is not going to demonstrate as well as I wanted it to. So it's just going to be more confusing.
But basically, in some languages that would break.
That will break in most object-oriented programming language. If I tried to refer to an instance variable that wasn't defined on the class or something, and I realize like that is just going to make a mess of things from my description. So
Basically, just
this is not a
really
C.
get in the habit of defining it up there, you'll be okay.
It's bad practice to just create instance variables. What I like to call willy-nilly. So, bad practice can get you into trouble, and it might be necessary sometimes. And just remember how easy it is to guard against. You could just set its default value. self.unicorn is equal to true here. And then that way, you never have to worry about a variable being undefined that you're going to go after later.
So if you're creating a method in a class, and you're like, okay, I'm going to need to change this variable here, but it doesn't exist, and then just run up and down it.
Exactly. That will protect you from most cases of that. All right. Wow. It's good questions.
Oh, actually, one more.
Let's do it.
So, by writing age, by defining an int, like, it's not necessarily looking for an integer. Like, it could be characters as far as it's concerned. So
Right.
How does it define, like, the name versus the age?
By the order.
Okay.
So we have age here. So when we create our fighter,
Okay.
it's going to take the first one and make that name. It's going to take the second one and make it age.
That makes sense.
Yeah.
And you're literally just passing Edwin through this fighter mold, and then you're assigning those two things, which are your definable variables.
Yeah, exactly. Yeah. Just think of it like a box. And you put Edwin, the name, in. You put age, the number, in. Or 32, the age, in. Inside of the box is your init. Those get tattooed onto the soul. And then it gets 3D printed when it gets... I'm just going all over the place with all of the metaphors. All right. Cool. Any more questions? All right. So before we jump into today's lecture, I want to talk just a little bit about Conway's Game of Life. And this is crazy because I saw my 7-year-old was watching this on Google, or not on Google, on YouTube. What's going on here? You see that?
I was about to ask the same thing.
You ever wonder, like, you probably never Googled this, but look at this. It's just like playing in the browser. It's just like one of those little Easter eggs, like if you Google Zerg Rush,
That's awesome. I love
and like
this.
they start just eating away. Oh, they had to take off the Zergs. It must have been a license issue or
Right,
something.
Yeah.
Yeah.
That's
You ever see this, Maddie? This is cool. Uh-oh, we got a Hydralisk coming in.
Stop
Oh, and
it.
you're supposed to hit the guys. You're supposed to kill them by clicking on them.
Take out Peregrine.
Like, what if you actually wanted to Google Zerg Rush? And, like, all your stuff just started disappearing like this.
I'm sure people do. There's so many builds for that.
Come on. Oh, jeez.
Oh, God.
We got overwhelmed from... Oh, wait, no, I remember. They eventually come back. Anyways, so yeah, Conway's Game of Life is a very small... It's actually beautiful in its simplicity. It's a way of defining a closed system that has rules for its adjacent neighbors. So if you could imagine a tic-tac-toe grid, you see like what this is Conway's Game of Life here. But if you could imagine like a tic-tac-toe grid, and let me make sure I've got the rules correct here. There are 4 rules. That's it. So we only have to code 4 rules. And so a cell is a box in that grid. Any box in that grid is referred to as a cell. So any live cell with fewer than 2 live neighbors dies as if by underpopulation. So that means if you have the center cell and there are less than 2 neighbors that are alive, that center cell will turn itself off. Then you have a live cell with 2 or 3 live neighbors will continue living. So if they have 2 or 3, so like up in the top right corner and then the top left corner, and they have the center cell on, they will stay alive for the next iteration. The live cell with more than 3 will die because of overpopulation. So if there are 4, now in a tic-tac-toe grid, there are 9 squares. So if you subtract 1 for the center square, which is the node, that means that there are 8 around the center square. So if 4 of those are populated with a on node, then that means that the center will turn itself off through the next iteration. And each one of these cells goes through this check. And then any dead cell with exactly 3 live neighbors becomes a live cell. So if there's exactly 3 neighbors around a dead cell, then that cell will turn itself back on. So this is a really interesting form of a simulation. it's not new. I mean, around 1940. The amazing thing about this is that people are still in 2018 finding interesting patterns within the within the design. So like people have found how to make repeatable structures. They've figured out how to make these like little rockets launch out of the designs. And what they do is they seed they will seed it with starting dots. So with a given game board of this state, they could do something like we are going to generate little rockets that fly, or they call them gliders. Like you can create entire factories that build things just from these rules. And because of these rules, you can see that like a still life, imagine that a 4 square cube, that like each cell abides by all the rules. So they're all on, like if you looked at this center one and just looked at these 9 cells around it, or the 8 cells around it, there's 3. So that means it's not going to turn on, it's not going to turn off. And the same goes for all of these. So a perfect square, a 2x2 square, will just stay alive indefinitely until something else gets into its space and it will totally screw everything up. You got beehives, boats, all sorts of cool things. You have oscillators, which are really neat. So like they will turn off and on, but they won't really morph their shape until they're interacted with. I mean, people like do master's and PhD level studies of what you can do with these. People do them on interesting shapes. Like you can do it on a hex grid. You can do it on in a circle space. I've even seen one was what's it? Conway's Game of Life in Conway's Game of Life. It starts out with these gliders, and then the gliders wind up. Here, let's speed it up a little bit. So the gliders, as you're zooming out, are intersecting with each other, turning off. They're forming this kind of weird-looking structure. And as you zoom out, you'll see that. Oh, just wait for it. Just wait for it. They form their own cells. And those cells themselves abide by these rules when you zoom out far enough.
That's epic.
Of course, the time scale has been sped up quite a lot.
That takes so much time.
Yeah. So that's going to be kind of what we're looking at today. If we don't complete it, that's fine. Really, the adventure is in the journey, and however far we can get to it, the better. And what really we're going to do is we're going to create 2 classes. We're going to create a board class that is able to create all of the nodes, and then we're going to create a node class. And a node class is going to be the dumbest class you ever write. A node class can know 2 things. What do you think those 2 things are? Is it alive or is it dead? And the board is going to have the responsibility to look at each node and then see what are the spots around the node. Like, are they alive? Are they dead? And it can get kind of funky, but yeah, it's going to look around each individual node. It's going to count all of the live squares around it. It will go to the rule set. It'll say, is it 2? Is it 3? Is it 0? Does this need to turn on? Does it need to turn off? And then it will wind up telling the node, hey, you are a node and you should die. And so we're going to do this in a couple iterations. Probably before break, what we're going to do is we're going to create our classes, and we're going to try to create a board. If we can create a board full of nodes and then output it to the screen, then we can take a break. So the relationship between these 2 classes is very important, because the node doesn't know who's above it. The board knows that kind of information. Now, what we could do is we could think about this design in a bunch of different ways. Maybe the board could pass the state into the node of like, hey, this is how many neighbors you have. You decide whether or not you're going to be alive or not. We can make all of those decisions ourselves. What's the best way to do it? We're not here to adventure into that. We're here to adventure into the design and the decisions that we make. We have to kind of live with, and I'll keep us on the rails, but the design of everything is the important part, because really what we're doing is we're practicing how do we relate little bits of data, and that's going to be super important next week and through the rest of the cohort, because bits of data that we're relating are going to be eventually not necessarily nodes that are on or off, but it's going to be in a database, and it's going to be like usernames and passwords, and we're going to be relating these things, or it's going to be like how many tweets has this user made when we make like a Twitter clone. So all very important things, and we just need to make sure that we understand how things can relate and work together. So we've got 2 classes. I'm going to go ahead and jump into Atom now, and I'm going to make a new file in week 2. Week 2 is we're going to say day_2. I'm going to say GOL for Game of Life. I think, as this grows, we might be able to set the classes into another file, like a gol.py file, and import them in. I think that might be fine. But as of right now, like when I'm in the sketchbook phase, like any artist will, like they'll just break out the sketchbook, grab their cheap pencils, and they'll start going. And when they're ready to actually finalize, they'll get out the tracing paper and the real expensive markers, and then they'll do that. So that's going to be our process. Let's just sketch out an idea and see how it works. So I'm going to first off put a couple of comments. So this is Game of Life. We know we probably need 2 classes. We need a board and a node. Some initial questions that I might have had were, does board do all the work? Can node decide if it lives or dies? What does node need to know? How can it know it? So when you're doing object-oriented design, sometimes you have to put yourself in the place of the object and say, if I were a node, where would I be? No, but seriously, when you've got, like if you've got a board of, say, 10 nodes, well, that wouldn't work. So it was a 10 by 10, 100 nodes, a 10 by 10 grid. That means that each individual one of those nodes is separate from the other. They're not linked in any way. So how can a node know if it needs to turn itself on or off? It's an interesting question, right? Like there's many answers to this. I could get 5 different senior level programmers in here and have 5 completely different answers of how to implement this. So I don't want you to think that this is like on the rails. We are going to have a very rehearsed process through this. I want us to kind of get in the dirt here and think about what does a node need to know and how can it do it? So my initial idea is that a node shouldn't know anything. That's one of the ideas, is that a node can be completely naive, and a node can expose the ability for it to live or die. So either so the outside board can then look at an individual node, know the 9 that are around it, and say, or the 8 that are around it, and say, you need to die. And so it says, node, kill yourself, or node, turn yourself back on. And then the node can follow that rule, which by design would load a ton of work into our board, and our node would do almost nothing. That's one idea. Another idea is that we can pass it, like the board can pass in, I guess we could say, like a matrix into the node, and then the node can count up how many of those nodes are alive, or are they dead. This means that the board doesn't really do all that much work. It sort of is just kind of an observe and report kind of role, kind of like a mall cop. Like they're just going to say what's going on and let the authorities handle it. I didn't mean that to like slight mall cops or anything like that, but like, they're not the ones that are actually going to take the person down to the station and book them at that point. So our board would go through each individual cell and will say, I don't care what the ones that are around you are, but I'm going to collect them and I'm going to give them to the center node, and the center node will take that information and it'll do what it wants with it. That's another implementation idea. Does anybody else have any other ideas? I can't really kind of think of any other. Like, the only other way that I think that could work is that, like, the board passes a copy of itself into each node, and then the node looks at everything, it takes its position, and then decides if it's on or off again. I don't really like that, because that... You remember in Ghostbusters when they say don't cross the streams? That is very much crossing the streams, where you have a board that sends a copy of itself into the node. Like, just think of that from, like, a physical standpoint. Extra work and really confusing. Like, in order for you to find your way around the building, instead of looking at the directory, the building winds up putting a copy of itself into your head, and you're just like, okay, now I know my way around, because your brain is able to figure it out when you have the... Like, it doesn't make... Maybe eventually that will make sense in science fiction. But right now, like, that's really convoluted way of making it work. It can work that way. We could do that. That is an option that we could do. So instead of exploring all the esoteric and, like, difficult to implement ways to do it, let's just start taking a stab at it. Like, let's start with the naive way. And if we find that that's really painful, like, we can pivot. We can say, you know what, that naive way was way too much work on the board. Let's offload some of that work into the node, and let's see how that changes our program. So let's start with our code. Let's create the node first. And what I want the node to be able to do is to be able to set its life state one way or the other. So its life state, let's define it in the init. Maybe we can have it, like, randomly be alive. Like, what state do you want it to be in when you create it? When a node is born, do you want them all to turn on, or do you want them all to be off, and we have to manually go through and turn them on? Or should a node just be like, I was lucky, I live, or I'm not lucky, I wasn't alive when I got created?
Assign them all dead. Probably sounds easier from, like, a mental perspective.
Okay. So let's set our self dot, let's say life equal to false. Because that's a Boolean, right? Just alive or dead. And then I'm going to make two helper methods here. I'm going to make one that says def live. And that's going to say self.life is equal to true. Let's say self def.die is equal to self.life is equal to false. You know, very, very basic stuff going on here. And then what I want to do also is I want to make a dunder_stir method, because when I print out a node, we might have to do this in a repr. That's fine. But when we print out a node, I want it to show that it's alive or dead somehow. And so if it's alive, I want to show an X. And if it's dead, I want to show a space. Because if it's dead, it's just going to take up blank space. So what I'm going to do is I'm going to, in my dunder_stir, how would you code that, by the way? If it's alive, show an X, or return an X. I just told you.
If self.life, then print X. Else print.
Well, since we're in a dunder_stir, instead of printing, I'm just going to return like X. Because the dunder_stir wants to give back the string. It needs to return a string. If we just print in there, it won't work. So and then the else, we're going to say return space. Okay. So down here in our program, let's go ahead and make a node. Let's say X is equal to a node, and let's print X. What would I expect to see when I print node here? An empty space. Okay, so let's run that. I need to cd into my week 2 directory and run Python day 2 game of life. And I do see a space. I mean, I don't technically see it, but it's there. So let's say x.live, and then let's print off that, see if we get that underscore. Sweet. Or not an underscore, an X. So I know that when a node is alive, it will show an X. I know when it's not alive, it will probably show just a space. That's good, right? We could do that. So,
Question.
yeah.
In the string, why are you able to just define it if self.life, as opposed to if it's false to this action?
So this is because just when you don't have an explicit condition, like if self.life is double equal false, this will look at the falsiness of the variable that's underneath self.life. So since self.life is a Boolean, it's a shortcut essentially that I could say, you know what, false is falsy. It's also useful, like if you have a string that might be empty or populated, you could just say if self.myString, and if that's going to be empty or populated, if it's empty, it will be false. But you absolutely could do if self.life is double equal to true. Like that's just as fine and readable as well. I'll accept that. So everything still works, especially when a node is alive. Okay. So if I want to create 10 nodes, how would I do that? A for loop? So if I say for underscore in range 10.
Why are you doing underscore there?
Because I really don't care, because this underscore will give me the number that it's iterating through, like the 0, 1, 2, 3, 4, 5. I don't really care about that. I'm considering it a throwaway variable, so I'm using an underscore there, which is a convention in Python. Like if you ever, I could say this is my number here, but I'm never going to use my number in that for loop or after, so I'm going to throw it away just by saying underscore. And that is, that's perfectly valid, and it's expected. So I can create nodes, right? I can say node open and closed. What do I want to do with those nodes? I'm going to need to, let's put them into a list somewhere. So I'm going to say row is equal to empty list. Then I'm going to say row.append node. So that's taking my empty list, and it's appending a node to it 10 times.
What exactly does append?
It will add it to the end of the list. So a list being a collection, it's essentially if these 3 tables represent a list of 3 tables, when I say append a table, we're just going to grab another one and we're going to plop it right to the end of it.
So you don't actually need to name those nodes anything?
Not really, because we're just going to make them and send them into the list, and we can refer to them by location. Any errors? Nope. And if outside of that for loop, if I print the row, what do we see? That's not good. That's not very pretty at all, right? Pretty ugly. Well, we can actually change stir to repr if we want. Whoa. Yeah, so I could say dunder repr. I can change my dunder string to dunder repr, and that will work when I print off the list. So you can see I have a bunch of empty things. Okay, so we've got one row of the game of life. But, so have we just started creating the board? We probably don't want to go too far down this rabbit hole. This was a good way to practice, say how do I create a bunch of stuff. So in order to create a board, we're probably going to want to start a class. A new class, at least. And that new class is going to be called board. And when we create it in the init, I pretty much just want to populate a board of a fixed size. Maybe we just do a 10 by 10 first off. I would say a 10 by 10, and I want to create 100 nodes in there, in each one. Sorry, I'm just thinking. Yep, that's where we get to the double for loop, because each row is going to create, because this is what's going to be referred to as a 2-dimensional data structure. It's a list of lists. And that will look a little funky, but I'll show you how it works. So let's create a class right under our node. This class is going to be called board.
The class's positions have no bearing as to.
In this case, they do. So if you defined the board above node, and then you tried to refer to node inside of board, not going to work. So on our board, I'm going to do a def underscore init. And since this is the code that's created, or that's called when we create the board, I want the board to go through and create a board of a certain size. So I want my size, let's do it like this. We're going to pass in an optional size variable of 10. Now, we haven't talked about keyword arguments too much, but when you have this where it says size is equal to 10, what that defines is a default value inside of this method. So you may or may not have to pass it in. So that means that when you call a board, you can just say, I want a new open and closed board. And if you don't give it an explicit size in its arguments, it will just default to 10. And since I'm going to make a board that's a square, I don't need like an X size or a Y size. I just need 10. So check this out, if you will. I'm just going to rough scaffold this out. I'm going to say I'm going to say row. Actually, let's say row count in range of size. So row count in range of size, that will tell us what row we're on. And then I'm going to do another for loop that says for column count in range of size. Now this is going to look kind of tricky here, but I'm just going to print an X. No, let's not confuse that with notes. I'm going to print an O. And then at the end of the print function, I'm going to add a comma. I'm going to say end is equal to empty space. So that makes it, so when you by default call the print function, it puts a new line for every print function. And when you put that empty space there, it will, how do I say this? It will not go to the new line for every print that's called. So let's watch what happens when I create a new board. I'm going to erase this code here. So when I say I want to create a new board, I don't even need to print or anything. Just say board open and closed. Watch what happens when I run my code. That doesn't look like a board to me, does it? I'm glad it doesn't look like a board to you. I would have to question what. I mean, maybe it does look like a board, but we need to do a new line, right? At every 10th one, we need to make a new line. So go ahead.
So basically, we start a new row, and then for range of 10, it's going to create going across.
Mm-hmm.
So basically, after that second for loop, that's where we can break the line.
So I should just do a print here. Because remember I said a print by default will just put an empty line, a new line at the end of it. So if we just do an empty print.
Well, maybe it needs to be an if. Yeah, if column count equals 10, then print blank space.
If column count is equal to 10, what happens if the column count is equal to 10? Will column count ever technically equal 10?
No. Well, column count equals 9. But that needs to be an if inside the second for. So if column count equals 9, then print a new line.
So when you go through an entire for loop, what happens? Like when you get done with the for loop, what will happen to the for loop? It goes down to the next line, right? What happens at this line right here? What does just an empty print do?
Yeah, that'll give you a new line.
And then it comes back up. So then this.
Check for that. Gotcha.
So that print thing is still right.
And in fact, since this isn't really a square, let's do a little bit more formatting. So let's put like 2 spaces after that O. So it's O space space. That looks like a square to me. Okay. So this is an interesting thing here. I want to show this in Python Visualizer because this is really funky. So I'm going to say size is equal to 10. And yeah, we're going to visualize this because nested for loops can really break your brain. So let's visualize this execution. And I'm going to watch the output over here. Don't watch the frames or the objects. And notice how many steps it has to go through, 222. So we're going to watch it happen probably just for a couple of rows, then we're going to be done with it. So it defines size, and now range of size will give us a list between 0 and 9. And row count will start at 0. The first time row count goes through, the first thing it hits is another for loop. And that for loop says, I'm going to go through 10 times. And that's the column. So it's almost like if you could think of the first time the first loop goes, it's the first row. And then inside of that inner for loop, it then goes bang, 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 bang. It goes through each of the columns. So watch what happens. So the first print that it hits, boom. It goes back up to the inner for loop. Boom. Boom. So it's going to go through all of these prints until it gets to, we're getting there, so notice that the column count's around 7. Once that column count hits 9, the for loop will be done. Oh, you know what? I did not, womp womp. I didn't grab this empty print, so it's not going to go to the new line. All right, so just bear with me, folks. Okay, there we go. So that has to be outside of this inner for loop. Let's try this again. Okay, now let's watch what happens. We're at column count 8. We're at column count 9. Notice that now it drops down to this print. It will print the new line, go up to the next row. It'll up the row count to 1. And then this line will reset the column count to 0. And it will start all over again. So that's how a nested for loop will work. Is that it will start with the most inner loop, go through it, be done, go to the bottom, and it will start up at the next one that's outside of it. So you can nest for loops, as many as you want, indefinitely. But you can really increase the amount of work your computer has to do. Like you could say, I want to nest these for loops 10 deep, and each one of them has 1,000 to do. I think that's essentially like 1,000 to the 10th power of iterations, because it goes up exponentially. Right? Is that correct? I don't know. It's too yeah, there you go. It sounded right. Joel the math man get you the right math here. Not that the math matters, but it's an important way to kind of think about the complexity. And complexity, I was listening to a podcast, and there was this really smart sounding guy who was talking about how complexity equates to the amount of time something takes to complete. And I had a problem with that because, time is relative, is what I just wanted to say to this person. Like the amount of time that it takes to run on my MacBook compared to my 486 back when I was in high school are very different. I think what complexity is a better measure of, that kind of thing, is how many steps are involved in that process. So this is, for every inner for loop, there is that amount of more work that it has to do. So if I only had one for loop, that would just be 10 iterations. That would be 10 things that it has to do. If there is a nested for loop, it takes that 10 and then multiplies it by 10 more. And then if there's another inner for loop, it takes that 100 and then multiplies that 100 by 10. So you can kind of see that like it increases the amount of steps. Not possible, like, sure, we can probably say it increases the amount of time, but it's on a microscopic scale at that point. I think complex. So yeah, so we can go forward, and this is essentially just what it's doing. Is it's just very quickly. Okay, so we've got our rows and columns to print out. That's cool. I'm going to go ahead and cancel that. But instead of printing, what I want to do is I want to create a node. And I want to put that node into a list. And when you're dealing with rows and columns, each row is going to be its own list. And then what you do at the very end of that for loop, instead of doing a new print statement, is you take that list that was just created as that row, and you append it into another list. So let's visualize this out. Actually, let me see here. Please tell me it didn't go away. Nope, it didn't go away. So let's code this in Visualizer, and then let's just copy it into our code. So if I define size is 10, and I have my board is equal to an empty list, what I want to do is I want to create a new row. Now notice that I didn't make my row out here. My board stays out in the ether. The row, however, is going to be created every time we iterate through this row outer loop. Because every row we get to, we want a new blank array. And what I'm going to do here is I'm going to say row.append a string of 0 or O space. So when we look at this code, it's the first for loop hits. It says, okay, we're in the first row. Create an empty row array or list, and then started throwing a bunch of strings into it. And then when that's done, because that's going to do all of the columns at once, when it's done, we want to say board.append our row. So that's saying, hey, our board, we have a new row to put in there. So we're like taking that whole shelf and we're putting it one after the other.
So essentially you're reducing the complexity because it's defining a row as 10 and then you're only printing 10 of those?
Yes. Yes. Well, the complexity isn't necessarily being reduced. The complexity is being managed inside of this for loop. Like I'm not going other places to say, hey, I want to create a board, and I'm not going this is a very, it's not a very crazy way of doing it. But let's visualize what happens here. So let's now, instead, I don't have any prints, but let's pay attention to the global frame of what it looks like. So if I have a size of 10 and my board is an empty list, my row count is 0, row is now an empty list. Now pay attention to the board and the empty list. My list now is going to contain a bunch of items. So it's filling up the row first. Like it's saying, I'm going to put everything into this row. We're almost there. There we go. So we have the entire row created. Now we're going to take that entire row, we're going to drop it into the board. So let's go down 1. So now our board, this is not a really great way to visualize it because it's going to create another list. Then it's going to append that to my board. And that's going to get out of control quite quickly. So I'm just going to let this run a little bit. This is actually kind of nice, but it's not how I was hoping it would show. So let's take a look here. So my board contains 3 or 4 lists inside of it, which this is the rows. I was really hoping it would be like this instead of horizontal. But we can see it here. They're staggered a little bit, but row 1, row 2, row 3, row 4. We have made a grid by doing this. So I'm going to go ahead and I'm just going to copy this. Oh, I can't copy it, can I? I need to go edit it. Because that's good code right there. And I will paste that into Slack. Actually, you know what? I'm going to paste everything we've got into Slack right now. So this is our working state at 10:10. This is what happens. This is where we are at. But we don't want to append a O space. What do we want to append that space? The node. Here we go. Unfortunately, though, this isn't setting anything. Like, if I was to just run this and then I wanted to, like, print off, like, print, if I said x is equal to board and I said I want to print the x dot board, that's not going to work. And it's because I've made a silly mistake right now. So what have I not done to make that possible?
Board needs to be self.board.
Correct. Board needs to be self.board, because if it's not self.board, board will just get thrown away. Like when I create this class instance here, it goes through the init, it will do all of this work and throw it away. It will not be possible to get any of that data back. So what we need to do is we need to say, hey, you know what? I want to put my board, and I need to change it here as well. I need to say self.board. I want to put that board into my lifeboat. I want to attach this board to the instance's soul, so that later on, I want to see it. So I temporarily named this variable x is equal to board, and then I asked for the x.board. So let's take a look at what that looks like. It's not pretty, but there are rows. This is a row, and each one of these commas is a column. It's not too bad. What would be a nice way to see the board? Like, I just want to see the board. Like, can I just print x?
We need to print where it would look nice. We would need a for loop to iterate through the indexes of the board.
Exactly, just kind of like how we started with this here. But I'm only seeing this board object with the memory address, so what do I need to do next? Repr? In this case, we would want to define a dunder stir.
Okay. What is the difference between when you would use repr and stir?
Repr, there's big differences between the two, but between the node and the board is that repr is going to be the string representation of this instance. And the reason we use the repr is because this node is put into a list. And if we were to just print the variable, we would want to use stir. But because we're printing sort of a side effect, like when you print the list, it's printing the list. It's not printing each individual node inside of that list. And so to save time and memory, when you print an item that's inside, like an object that's inside of a list, it just goes to the repr because it's much faster for Python to do that. So we say we want to override the repr because we're looking at it inside of a list. Now, we're not, like, this isn't going to be long-term. Like maybe, sure, but I'm probably going to want to use the stir. But we'll come back to that. This is just for demonstration purposes earlier. So, but in our board, though, our board, for example, I would want to do the def __ stir. And like you said, John, I want to do that double iterate with prints. Or, oh, you know what? We're going to have to
be a double. Would it be a double iterate or just a single iterate? Print
each row.
Index 1 and then index 2.
Yeah, we could do that. So if we said like for row in self.board, and then we just printed the row. Now the problem with this, like I just said this about printing in a dunder stir, is that it still needs to return a string. So we should probably just like return an empty string so that it's happy. Because if we return none, it's not going to be happy.
So, okay.
Because we're printing in the dunder stir.
Right. Okay, I got
So we also need to return a string from the dunder stir. Like that's a requirement.
And that's just like a placeholder. It's not actually.
Yeah.
It's not something you're going to use.
Exactly. We're just using that as a placeholder. So look at that. Look at my board. We did it.
So if we ran this, is that going to still be 256 steps or whatever in the visualizer?
For the print? No, it's going to be double that. Well, it's not going to be double that. It's going to be like 1/3 more that.
Without backtracking too much, you still have the visualizer open.
Yeah, I think so.
So I'm just a little bit curious as to why, when we did this, it was still 256 like steps. Didn't we define the row as being a set value of 8? So shouldn't it just be like, 10? So shouldn't it just be like, so building the row takes 10, and then shouldn't it just be 11, 12, 13, 14, 15? Like, it's adding the lists.
Well,
in a row?
when it counts the steps, it counts every line of code that it has to go through.
So
So
that's just how it processes it.
yeah, so I wouldn't pay too much attention to that 243 number, because like that's one step, that's another step, that's another step. Like every time that arrow moves, it's another step. So yeah, you're right. Like in terms of complexity, we're pretty much making we're making a row here. Then we are iterating over the size of that row, and we're putting things into it. So that would be 10 steps. And then at the very bottom, we're saying, well, I want to add that in there. So then it goes back up here. Make a new row. Start throwing values into that row and put that row onto there. So yeah, that would be, if it was just the append items to the inner row and then send that row, like that would be 110 steps essentially. But then on top of that 110 steps, it also needs to call these two rows. Like it's per line by line. But yeah, in terms of complexity, it's 110 steps to do that. Like if you wanted to add a dimension that was a size 10, it would be 10 times more than that. Okay, so but look what we got. We have a board. They're all dead though. So how can we tell if it's if like what if we want our board to be kind of alive? How would we do that? What would be the easiest way to do that?
I mean, the easiest way would be to change the default state in the node.
So right here, like change that to true.
And it's all going to be alive.
Works well too. What if we had the node make that decision that it was alive or dead? What if we what if we just said we're going to be like a random choice of true or false whether or not this node is alive when it starts. So I'm going to import random here. And then self.life is going to be random.choice, and then we're going to pass true and false to it. As a list. You have to pass true and false as a list into random.choice. So it like takes one or two. Okay, now let's look at what our board looks like. Now we got a board.
If we wanted to print that without the brackets and the commas,
Down here?
so we would need to change how we print it.
Right, because we're just printing the row, and that row is going to...
So that we can do the double for loop and then actually print the node instead of...
Well, we've done a way that's better than the double for loop so far. How would you do that? Nope, other way. Split converts a string to a list. How do you convert a list to a string? Starts with J, rhymes with. There you go. Yeah. So what we want to do is we want to do like space dot join row. What's this error? You didn't get that?
No, I got that.
You got that?
So it would need to be... That's because we haven't set the string for the node. We set the repr. And we're calling join.row, which is native. So it's what you're talking about.
Expected a string instance. Really? Is that the thing? Do we need to just change this to stir? No. There's something going on here. Row is of type list. Oh.
We need to set a variable in that for loop equal to an empty string and then say that variable dot join row. Or would that not? I guess that wouldn't matter.
You know what? I think I know what we can do. We want to manually call, so this is going to look weird, but we can manually call the repr method on the row. No, we can't do that. Oh, okay. So I think the double for loop is going to be the most straightforward thing here, because the problem is that it's not. So the strength.
Well, actually, because it would have to be on a row index. We'd have to actually call the row index, right?
Yeah, to do that repr. How did that not work though? That should have worked. Well, I guess it didn't. So, but we're close though. I mean, we could say, let's get rid of that join, and let's say for column in row. And then here we would just print the column, which would be the node. And we'd say that the end is an empty string. And then outside of that for loop, we would just say print open and close again. So that would work. Let's put 3 spaces per column. There we go. So we're making a random board every time. Look at that. But it looks like that's going to be way overpopulated, right? Is that going to seem overpopulated to you? Like, that's a lot of things. What if, let's think of this from a statistical standpoint. What if I wanted to make the chance of life even rarer in my board? I can do that with one tiny thing. So let's look at the code that decides if life is going to be alive or dead.
We could just add more falses to that list.
Yes, we make true more of a rare thing. So if, statistically speaking, life has a 1/3 chance of being alive. So watch, our board will be more sparse this time around. See that? Look at between the 2 runs. We could also
be able to like apply a multiplier to that instead of typing out false a bunch of times because the list, right?
you could add a multiplier. Like we could say it's true, and then we can do, like we could say plus equals false times 3. Oh, that's not going to work, huh? I thought you could do that. Don't lie to me, Python. You could say, oh wait, no, you don't do plus equals. You can only concatenate list. Come on, we can do this. So you can concatenate 2 lists together. Not what I would have expected.
What if you do the times 3 outside of the bracket?
Oh yeah, that would work. There you go. So we can do. So yeah, so we could read. This could be a little funky to read, but yeah, you can do that. There you go. And now you can add it like to 10. Now it's like super rare. All of these cells would die. Let's say 100. There's only one. That's 110. There's a 1 in 100 chance. Statistically speaking,
It's very
how many cells do we have? We have 100 cells, and there's 1 alive. Oh, I have a statistical outlier. Life found a way.
Re-regulated.
Of course, when you run this enough times, it will show up as 1 in 100. It uses I believe it's a uniform distribution, so it's fairly predictable. Okay, so let's take a break there, because we have our board of, I'm going to change this to be false. And let's just maybe make it a 3. There you go. That looks like a good seed for a board. When we come back, we are going to add some functionality to the board so that it can see whether or not a node is going to be alive or dead.